Video is for practice on average value and fundamental theorem of calculus part 1. This part is not anywhere really in your notes, but we just wanted to make sure you had the chance to review what the difference between definite and indefinite integrals are. I will tell you first what each one looks like. A definite integral looks something like this with numbers on top and bottom and some function here, while an indefinite integral looks basically the same thing, but no limits of integration. So now, because as many of you know, my handwriting is terrible, I'll go ahead and just put some characteristics in here. A definite integral has limits of integration. And it also has, just put a bullet point in here, just tap that. And it also has results in a number. And FTC can be applied. That last part of the fundamental theorem of calculus being applied implies this, that the integral from a to b of f of x dx is equal to the antiderivative. The antiderivative is net change between a and b. For an indefinite integral. And indefinite integral has no limits of integration. It results in a family of functions with that plus c, or in my class we say plus communism, and FTC cannot be applied. I'm going to add up here that this is also resulting in an antiderivative. So please take your time to go ahead and copy these down. I'm just going to reduce the font here so we can get this all on one screen. And we'll go to the next slide. The fundamental theorem of calculus says that if a function is continuous or integrable on its closed interval, then we can have some function where x equals a to x equals b of a function is equal to the net change of the antiderivative. And that is called net change of the antiderivative. We also said that this equation is not static, it is dynamic. We can move it around if we need to. Well, let me finish writing out all these letters first before I go on here. I'm going to write on the side here small letters, and I did this in my class, that we could also write out that x equals a to x equals b of f prime of x dx, and that's equal to little f of b minus little f of a. And we also wrote out in my class that we could have the integral from x equals a to x equals b of f double prime of x dx, and that's equal to f prime of b minus f prime of a. So again, just want to make sure you're aware that the fundamental theorem of calculus here could be manipulated in different ways. And then finally, we said that this equation is not static, it's dynamic, meaning that we can take this equation and do this with it. We could add the f of a over to the other side and have f of a plus the integral from a to b of f of x dx equal big F of b. This is a powerful equation because it says that there is some start value, some initial condition, plus how much everything is changing by. Let's just do a different color here. an accumulation of change. And if you do the starting value and accumulate how much change you've had and add onto the starting value, what you're left with is a ending value. That's all about the fundamental theorem of calculus. The next part is the average value. And if you see the word average, again, there's a good chance that you're going to have to use this formula in some way, where you are either solving for C or you're just calculating the average value. We're going to give you more and more free response questions over time, and I want to point out before I start the problem that these solutions are easily findable online, and I strongly recommend that you, don't look up the answer right away, man. Like allow yourself to process the problem and think about the problem. And if you're crunched on time, don't do the problem. Make sure you set some time aside so you can actually look at the problem and think about it, and you can have a good attempt at it. I want to try to limit as much as possible you trying to show how much you know because you looked at an answer that was provided to you. Like, we want your real knowledge here. So when I do number 2, I'm not going to look at the key at all. I'm going to solve the problem as I see it. And then you can check my answers at the end, but they should be correct for the most part, I hope. I really hope. A. And by the way, if you'd like to pause now and try these problems on your own and then watch and see how you did, that's fine as well. Number 2 says, and it's from 2011, as a pot of tea cools, the temperature of the tea is modeled by a differentiable function h from the closed interval 0 to 10, where t is measured in minutes and temperature h of t is measured in degrees Celsius. Values of h of t and selected values of time are shown in the table above. Use the data in the table to approximate the rate at which the temperature changing at time t equals 3.5. Key word here, rate, which means I need something minus something over something minus something. 3.5 falls right in between here. So what I'm going to do then is use h of 5 minus h of 2 over 5 minus 2. These are common questions. The reason that I'm using this is because, again, I want to approximate a rate, and I don't know the instantaneous rate at 3.5, so I have to approximate it. And that idea is using the secant line. I'm just going to sketch some arbitrary graph here. I would have to use the secant line to approximate what actually happens at 3.5 in between 2 and 5. So it may not be the exact slope, it might not be the exact rate at t equals 3.5, but I'm using the slope of the secant line, or the average rate of change, to approximate tangent line. Slope of the tangent line. And then I'm going to go ahead and just plug in those values. H of 5 is going to be, and this is I think it's a calculator problem. It's number 2, so you could use a calculator here. H of 5 is going to be 52 minus 60 over 3. You could use a calculator here if you want. This is negative 8 over 3, or negative 2.6 repeating. And they do want, I always would put units. So the units here are going to be negative 2.6, I think it's degrees Fahrenheit, Celsius. If they wanted an explanation as to what this actually meant, we would say that at t equals 3.5, the temperature of t is decreasing because we have negative rate is decreasing at a rate of 2.6 degrees Celsius per minute. And I'm going to just add a keyword here, approximately decreasing. Or is decreasing at approximately? Okay, so that's the answer here. Let me just see what's behind this pink box here. And it has exactly what we needed here. Beautiful. Okay, so this would have been 1 point for that answer. And I'm going to go to the next question. I just want to make sure you have a clean way of seeing all the printed out work that AP provided for this problem. Number 2b. Using correct units, explain the meaning of 1/10 times the integral from 0 to 10 of h of t. Use the trapezoidal sum. We have not gone over this word trapezoidal before. By the way, this is the same problem. It's just different parts, 4 parts usually. It says use a trapezoidal sum. We're going to do this in the coming weeks. A trapezoidal sum is equal to the left sum plus the right sum divided by 2. Notice also that this is 1/10 in front. The 1/10 implies that we're looking at an average here. So what I'm going to do is find a left sum. Left sums were going to be found by doing 2 minus 0 times 66. Plus 5 minus 2 times 60. And by the way, I need 4 subintervals. So you will see 4 calculations here. So I started writing it off for you, and then it took too long, so I just did all the work here. If you need a pause to write down what you see, please do. I tried to color code everything so that way it would match up with what you see here. Again, the left side is the blue, green, the purple, and the red. The right side is the light blue, the yellow, the gold, the pink, and the purple. And I added up both of those left and the right values, and I got a total of 1,059. 1,059 is that integral value. So I get the integral value I get is 1,059. Now it is divided by 2, so I need to do 1,059 divided by 2. Again, we'll do this in the coming weeks. And 1,059 divided by 2 is 529.5. So I need 1/10 of 529.5, which I believe is 52.95 degrees. The meaning, and I'll put that up here so I can kind of stay on one area here. The T, the pot of T, has a temperature, has an average temperature, and that's the key word, has an average temperature of 52.95 degrees on the interval, or for the first 10 minutes. Let's do for the first 10 minutes. Okay, and that's my answer for this one. And since I want to kind of move it along here, let's go to the next one. Evaluate and express the meaning. So this is a fundamental theorem calculus question. We have h of 10 minus h of 0. That's, again, the net change of the antiderivative. H of 10 is 43. This is for the evaluation part. H of 0 is 66. And 43 minus 66 is, I think, negative 23, but you could use a calculator to check it. And they want to know what this is. Well, this is saying that the net change of the temperature of the T Temperature T decreased 23 degrees from 0 minutes to 10 minutes. So that is for part C. And again, I didn't give you time to pause. So on the next one, if you need to, please pause so that way you can see it. Okay, so they said drop. And then for this one, I didn't show you the answer. I hope we got it correct. I think we did. It'd be embarrassing if we didn't. So that was all their work there for us, which again, they got us the same answer. And we had the same answer here. That was a 3-point problem. And then finally, 2D, at time t equals 0, biscuits with temperature 100 degrees were removed from an oven, taken out. Temperature of the biscuits at time t is modeled by a differential function of b. Using the given model, how much cooler are the biscuits than the t? Okay, so here they're telling us a little bit of two things. They want to know, using the given model at time t equals 10, how much cooler are the biscuits than the t? Well, the t, so my mind goes to this right away. Your mind might do something different. How much cooler are the biscuits than the t? The t here is 43 degrees at time t equals 10. But what we need to do is we need to find the temperature of the biscuits. And the temperature of the biscuits is going to have to be found with a calculator. And the way we're going to do that is they give us b prime of t. Well, b prime of t is a rate. So I'm going to use a different color here. For b prime of t is a rate. And if I integrate the rate, I get the temperature. So what I need to do is I need to integrate from 0, t equals 0 to t equals 10 of b prime of t. And I'm not going to try to do that by hand. I'm going to type that into my calculator and see what I get here. And I am almost done. So let me go ahead and just clear this. And let's go into a math 9. And we're going to do 0 to 10 of negative 13.84. No, that's not a negative. Don't use a minus for a negative. 4, and then we're doing e to the negative is 0.713. X dx. Now, you might be saying, wait a second, Mr. Lakin, that can't just be all of it. You're 100% right, that's not all of it, if you thought that. This is going to get how much the biscuit actually changed. This does not get us the actual temperature, and that's a very important idea. So when we integrate a rate, when we're finding that area of the rate, that only gets us how much the temperature changed of the biscuit. But we need a starting value. Okay, so this value was, and we'll use 3 decimal places, negative 65.817. That's an approximation. From 0 to 10 minutes, the temperature of that biscuit dropped 65.817. So the temperature of this biscuit then is 100 degrees minus that 65.817. And that is going to get us a 3, an 8, a 1, a 4, and a 3, I believe. You can check me if I'm wrong. Let me just go and do 100 plus that answer. Answer equals, yep, 34.182. 0.182. Okay, that's fine. So minus 65.817 is our answer here. I'm sorry, 34.183 degrees is the temperature of the biscuit. So now, how much cooler are the biscuits than the tea? We need to do one more thing. We need to do 43 minus this value. So now I'm going to do 43 minus that answer here. And that means the biscuits are 8.817 degrees cooler. Biscuits are 8.817 degrees cooler. And that is your answer for this problem. I'm going to go and check that we got it right. Oh, that doesn't look so good. And the final answer we have here that AP provided us with is going to be the same exact thing. Guys, thank you so much for watching. I hope this helped. I know the video was a little bit lengthy, but I hope that the time that I took to explain was worthwhile for you. We'll see you next time.